Today, we're digging into a mathematical cold case that's been sitting unsolved for nearly 100 years. It's called Artin's conjecture. And let me tell you, this isn't just about numbers. It's a full-on detective story about the hidden patterns that govern the infinite, wild world of prime numbers.
All right, let's get right into it. We're about to investigate a puzzle that has had mathematicians scratching their heads since 1927. It's a question about primes that, it seems so simple when you first hear it, but the solution has just always been just out of reach.
And right here, this is our first big clue. This is the hook for our entire investigation. What if the path to solving this incredibly deep mystery actually starts with something we all remember from school? A simple fraction. I mean, how is that even possible? Well, let's find out.
Okay, so to really get the mystery, we have to meet our main character, the primitive root. So imagine a prime number, let's say 7. Now pick another number, like 3. If you start taking powers of 3, so 3, 9, 27, and so on, and you look at the remainders when you divide by 7, you get this amazing sequence that cycles through every single number from 1 all the way to 6. In this case, 3 is like a master key that unlocks all the numbers for the prime 7.
And this is the heart of it. This is the whole conjecture. Back in 1927, a mathematician named Emil Artin suggested that for pretty much any number A you pick, it's going to act as a master key for an infinite number of primes. The problem? Well, proving it. Proving that this isn't just some crazy coincidence, but a fundamental rule that just keeps happening forever.
So, you might be asking, how in the world do you tackle an infinite problem? Well, we're going to pivot. We're going to come at this from a totally different, and honestly, a very visual angle. The repeating patterns you see in decimals. And yeah, this is where those simple fractions come roaring back into the story. We all know that 1/3 is just 0.333 repeating, right? It's a pattern of length 1. And 1/7 is 0.142857, which then repeats, a pattern of length 6. So what if we just went on a hunt? What if we just searched for the fraction with the longest repeating pattern we could possibly find? It turns out this simple, almost playful question is deeply, deeply connected to our mystery. So as we start looking for these record holder fractions, a pattern just jumps out at you. I mean, look at the denominators. 3, 7, 17, 19, they're all prime numbers. But even more amazing, for some of these, the length of the repeating part, the period, is exactly 1 less than the prime itself. Like for 1/7, the period is 6. For 1/17, it's 16. That connection is just too strong to be a coincidence. It really feels like we're onto something big here.
It feels like we are right on the verge of cracking this whole thing wide open. I mean, if we can just prove that this record-holding sequence goes on forever, we've solved it, right? Well, not so fast. Here comes the first major plot twist in our investigation.
The logic, it seems totally solid. The length of the repeating decimal for 1 divided by a prime, that is directly tied to our master key problem. So it feels like proving the periods can get infinitely long should be the exact same thing as proving our conjecture. But unfortunately, there's a really subtle and really crucial flaw in that thinking.
This slide just lays it all out, the critical difference. On the left, you've got unbounded growth. We can actually prove that. We can prove that the length of these decimal periods will just keep growing forever. They never hit a ceiling. But what Artin's conjecture actually requires is what's on the right, infinitely frequent saturation. See, it's not enough for the records to just keep growing. They have to hit the absolute maximum possible length, p-1, over and over and over again, an infinite number of times. And here it is, the big reveal. Just because the lengths of these decimal periods get bigger and bigger, that doesn't mean they ever have to hit that maximum value. It's totally possible for them to grow forever while always staying just a little bit short. Maybe it's, say, half the maximum length. And that means this whole decimal record holder path, well, it's a dead end for a direct proof. Okay, so if a direct search doesn't work, what's our next move? We flip the script, totally change our perspective. Instead of trying to find out why a number is a master key, we're going to investigate all the ways it can fail to be one. We're going on a trail of obstructions.
Think of it like a series of security checkpoints. For a number, let's say 10, to be a master key for a prime p, it has to pass every single security test. If it fails even one of them, boom, it's out. Each one of those potential failures is what mathematicians call an obstruction.
So here's how this obstruction gauntlet actually works. For any prime p we're interested in, we look at the number just below it, p-1. Then we break that number down into its own prime factors. and each one of those factors creates a brand new test that our candidate number, in this case 10, has to pass. So the more factors p-1 has, the longer and tougher this gauntlet becomes.
Now, this is where it gets really cool. If we just treat these tests like a game of chance, like they're independent probabilistic events, we can actually calculate the theoretical probability that a random prime will pass all of its tests. And that probability works out to a famous number called the Artin constant, which is about 0.3739.
So that's the theory. What happens when we just check the data? We can actually count. And when mathematicians checked the first 2 million primes, they found that the fraction of them that had 10 as a master key was 0.3750. I mean, look at those numbers. The agreement between theory and reality is it's breathtakingly close. This tells us that this whole obstruction model, it is absolutely on the right track.
Okay, so we have a model that predicts reality with unbelievable accuracy. Now we need a tool to make it all rigorous. We need to build a mathematical sieve. The idea is to filter out all the primes that have at least one obstruction, leaving behind only the ones that pass all the tests.
Now, sieve theory is a super powerful tool in number theory. But for a lot of famously hard problems, like the twin prime conjecture, these sieves eventually hit a wall. It's called the parity barrier. And parity just means whether a number is even or odd. This barrier is a fundamental flaw that basically prevents the sieve from telling the difference between numbers with an even number of prime factors and those with an odd number. And that limitation can stop a proof dead in its tracks.
But this is the breakthrough. The mathematical structure of the Artin problem is special. When you build a sieve for this specific problem, the way the obstructions are weighted gives it something called a dimension of 0. And what does that mean? It means there is no parity barrier. The fatal flaw that plagues all these other sieves it doesn't exist here. This tool can actually work. It can go all the way.
So the path is clear. The tool is right. We've filtered out the dead ends, and we have built a powerful machine to get the job done. After all of this work, this entire 100-year-old mystery has been cornered. It now rests on a single, final suspect.
And that's really the beauty of this whole approach. All of this complex machinery, the group theory, the sieve methods, all of it has managed to distill this enormous problem down to one last, much simpler question. It's all about the average behavior of prime factors for a very special family of numbers.
And this is the evidence. The final hypothesis is true only if that blue line on the graph, which represents the real data, stays small and well-behaved. And as you can plainly see, it does exactly that. As we test more and more and more numbers, the line actually trends downward, staying far away from any danger zone. The data is incredibly stable, and it strongly suggests this final piece of the puzzle is in fact true.
So, the case file is nearly closed. The evidence is it's overwhelming. The data is clear. All the signs are pointing to Artin's conjecture being true. But this brings us to a final, really fundamental question about the nature of math itself. In a world that demands absolute 100% certainty, is even the strongest evidence truly enough to call a case solved?